Hi, I'm Antonio Sala, and in this video we will discuss how to compute the time response of a circuit with a capacitor and two resistors. The input we are going to deal with will be a single sinusoidal pulse. We will use ideas from the Laplace transform domain, and in particular we will solve the problem via some superposition and time invariance properties without explicit use of the input Laplace transform. This is the circuit we are going to handle. Input will be this U of t power supply, and my output of interest will be the capacitor voltage. I have highlighted the four equations that constitute a first principle model of the system, details in another video. And from these equations, we can obtain a normalized state space representation, first order. Given numerical values, we get matrices A, B, C, D, in this case 1 by 1. And taking Laplace transform, we can obtain a model. In this way, some transfer function times the Laplace transform of the input plus some initial condition term, as here, from the state space matrices. So it's now the time to use that model to obtain the time response when the input is a sinusoidal pulse with this expression, whose plot is this one. So I have a half period of a 50 Hz sinusoidal wave, so it's a 10 millisecond pulse. In another video, we obtained the Laplace transform of the input pulse, so we could multiply this by the transfer function and carry out some operations. Indeed, it's a valid way to do. Just take care of this delay operator when doing the inverse transform, but I leave it to you. In here, we will use some superposition ideas in the following sense. Even when computing the Laplace transform, we realized that the blue half-period pulse was the sum of the red sinusoidal, whose Laplace transform was this one from Laplace tables, and the yellow one, whose Laplace transform was the same one except for multiplying by this delay operator. The sum of those two signals gave me the blue one, so this was the Laplace transform. But as my circuit is a linear time invariant system, I can do this superposition directly on the output. Why? Well, I know that the output to the yellow input will be exactly the same as the output to the red one, but delayed 0.1 seconds. So superposition would tell me that the sum of those two outputs will give me the output to the sine pulse. So it's kind of carrying out the same superpositions we did at the input side to compute U of S, now at the output side to compute the output directly in time domain. Let's go. The Laplace transform of the red sinusoidal will be U1S, a sinusoidal starting at t equals 0. Let us now compute the time response to 0 initial conditions by first computing the time response to the red sinusoid starting at t equals 0 till infinity. I get this y1, which if I were in a pen and paper examination, I would need to split this in a partial fraction expansion to avoid this correct but strange thing with lots of pi. I just will ask for variable precision arithmetic, so the partial fraction expansion is this thing. And then if I carry out inverse Laplace transform, this thing will end up yielding this exponential term, 102 It's because the polling here is in 102.5. We must divide by 2, numerator and denominator. Okay, and this factor, this is omega square, corresponds to a combination of cosinus and sinus once I look into Laplace transform tables. Indeed, 0.28 is the thing that multiplies cosinus because of the s here, and if I multiply and divide by 100 pi, then this coefficient will be the one yielding the sinus term. Hence, I got the response to the red sinusoid lasting forever, and if I plot it jointly with the input, I get this red thing. However, as the input is not a sinusoid, it stops there, then this red line is not the response I wish to obtain. My superposition argumentation tells me that the actual solution I am seeking, response to the blue pulse, will be the sum of the one I just computed plus the same one delayed 0.01 seconds. So this would be the final response in a pen and paper answer, where y1 is this thing I just computed. The original one responds to the red input plus the response to the delayed sinusoid, yellow one, the second fragment, 0 in the first half period, and then the same waveform but delayed, 0.01. So that would finish my exercise, but as I have MATLAB, I wish to plot it to see if I can get some intuition on what's happening. And indeed, with a little bit of bookkeeping, we can plot this stuff. This thing was named y1t, and then this expression is made by all this code in which I first multiply by the Heaviside function to make 0 the function for negative times, because otherwise the symbolic function understands the exponential as an exponential for positive and negative times. It's not true, so I must explicitly tell Symbolic Toolbox that this thing I obtained is valid only for positive times. Heaviside is the step function, 0 at negative times, 1 at positive time, so okay, this is the first step, and then the delay stuff is substituting t by t minus 0.01 to accomplish the delay. So this is the way to encode in MATLAB the yellow highlighted fragment of the solution. So once I have yt pulse, then I can just use fplot to plot it. And indeed, I obtain the red output superimposed to the pulse input. So we see that initially, while the pulse is active, then the capacitor is charging, and at the time the input voltage is below the capacitor 1, then it discharges. Well, in fact, if we are precise and we zoom in, it will start discharging a little, very little time before this crossover instant because of the leakage current, but okay, grossly speaking, it discharges when input tension gets below the capacitor 1. Of course, if this were a true rectifier with a diode, things would be very different. The thing is that, also important, we will exploit that fact in a second video with an alternative way of obtaining this solution. From this instant onwards, input is 0. So for sure this will be an exponential free response because I have no input, so this will be an exponential discharge of the capacitor. I will have 0.01 seconds of a fourth fragment and then an exponential discharge. So we obtained via Laplace transform the time response of a first-order electrical circuit to this single sinusoidal pulse. The response is the red line here. We didn't explicitly use the Laplace transform of the input, even if we know it, because we can realize that the same trick we used when crafting such Laplace transform can be used to obtain the output. Which is that trick? The concept of superposition of a sinusoidal and a delayed sinusoidal expressing the blue waveform, which translates to the superposition of the response to a sinusoidal and a delayed version of it, which ends up crafting the red solution. If initial conditions were non-zero, I would just need to add this term to the just obtained output. Indeed, for instance, with this initial capacitor voltage, that initial condition term will be this thing in the Laplace domain, and of course will be this exponential discharge of the capacitor free response in time domain. So if I add this to the previously computed response to the pulse, then I get the response with non-zero initial conditions. Here we have it, in which we start at 0.95. So again, we applied superposition to add the effect of non-zero initial charge. So this ends the video. Thanks for watching.